everyone. So in this video, we will talk about the superlattice peaks. You might heard about that in some of the X-ray diffraction pattern, you get the XRD peaks, and these peaks are called superlattice peaks. So let's take an example of Heusler alloy, which are very famous. So in the Heusler alloy, I opened this X-ray diffraction pattern of some Heusler material. Okay. So this is like 2 theta versus intensity plot. So in this, we can see that this 220, this is the main peak, which is also called the fundamental peaks. Okay. Then there are 2 more peaks at low angle. One peak is 111 reflection, and another is 200 reflection. So these 111 and 200 reflection in the Heusler materials are called superlattice reflections. So these 2 peaks, these peaks are called superlattice peaks. So today we will discuss about what are the superlattice peaks, okay, why they exist. So let's discuss this in detail. So let's start with the monoatomic FCC basis. Okay, so monoatomic means we are talking about that in this FCC lattice, there is only one type of atoms. One type of atoms. Okay, and that's why we are saying this is monoatomic. So in FCC, we know that there are 4 atoms per unit cell. Okay, and these all 4 atoms are one type. So let's say we have copper. Okay, so copper, which is distributing among the 4. So this is like all 4 atoms are of copper. So when we see what are the coordinates of these 4 atoms, so let's say first we put at a reference point. So the coordinates are, these coordinates we are saying U, V, and W. Okay. So UI, VI, WI. So one we fixed at the one of the corner, considered as a origin. Second is at the center of the face, and this is like half, half, 0. Third will go half, 0, half. And fourth will go at 0, half, half. So these are the coordinates of 4 atoms. Okay. So now if we calculate what is the structure factor. Okay. So structure factor is given by this formula. Okay. So FHKL, J equal to 1 to 4 because we have the 4 atoms. Small f here is the atomic factor, atomic form factor. Okay. And then we have, this can be derived, we have 2 pi I HKL. Here are the Miller indices. Okay. And UJ, VJ, and WJ are the coordinates of the atoms. Okay. Like here we define 0, 0, 0, half, 0, and so on. So if we put values of HKL and UVW, so we can calculate what is the structure factor for this particular peak. Okay, and that can tell whether this peak will be existing, whether we can see this in the XRD pattern or not. Okay, so that would be decided by the structure factor. So when we are putting the value of U, V, and W different coordinates, so our structure factor will be this. Okay, you can just put 0, 0, 0, then that will give you 1 because f we took common. And when you are putting half, half, comma 0, you will get this one, and this one. Okay, you can calculate it. And now if we calculate the structure factor for the 200 peak. Okay, so if we are calculating for the 200 peak, h equal to 2, k equal to 0, l equal to 0. So we found that this is equal to 4f. And now if we calculate the intensity is basically proportional to the amplitude of this structure factor. So this will give you 16f square. So basically, this is saying that 200 peak would be present there. Okay. And if we calculate the structure factor for 111 reflection, so similarly, again, we will calculate the structure factor, and this will give you again 4f. So intensity, you will get 16f square. So basically, if we see the XRD of, let's say this is 2 theta, this is intensity. So we would have 111, we would have 200, then 220, either odd, all odd, or all even. So we will these kind of the reflection. So basically here you see 111 and 200. Basically these are the fundamental reflections. Okay, so these are the fundamental peaks. These are always present. Okay, in FCC lattice, if we are talking about the monoatomic. Okay. Now, so, okay, this is the summary. So both 111 and 200 are the fundamental peaks. Now, if we talk about the Heusler materials, okay. So Heusler materials, let's say this is like X2 by Z type material. So X, Y, these are the transition metals, and Z is from the main group. So basically you have the 4 atoms, okay. And generally they show L21 structure. So if we calculate the scattering factor for this 200 and 111 for the Heusler alloy, so let's say that first all these 4 atoms, what are their coordinates? We need to distribute these at a different position of the unit cell, right? So let's say the bi atom, we are fixing at 0, 0, 0. Z atom goes to the half, half, half position. And the X atom goes to the 8C, 1 by 4, 1 by 4, 1 by 4. And 3 by 4, 3 by 4, 3 by 4. Okay. So this is just an example. You can distribute in the other ways also. Let's say Z you can put on the horizon and then distribute another. So just taking one configuration, okay, and saying, okay, these atoms are on these lattice positions, okay, Wyckoff positions. So now if we calculate what is the 200 reflection, structure factor for the 200 reflection, so basically you can calculate for putting just the value of HKL and the value of UVW, and then we can write down the what is the structure factor for 200. So this is the structure factor for 200, which comes 4 times Fy plus Fz minus 2Fx. Okay. And then if we know the structure factor, we can calculate the intensity. Okay. Now here, if we focus on the structure factor, it depends if X, Y, Z, they are going to their fixed position, right? They are going to their fixed position, then of course you will have F200 peaks. Suppose if they are swapping with the X atom, okay, if this is swapping with the X atom and this is swapping with the X atom, so basically this will be then 2Fx and minus 2Fx, okay. So this peak will disappear, okay. This reflection will not be present there if these Y and Z atoms are swapped with the X atom. If this Y atom and Z atom, they are also going to the X sides, and X is coming to this side. So basically, they are slipping there. They are going to each other's. Then you cannot actually say, okay, this is Y and this is Z. Okay. So there is no difference. Then this 200 reflection will not be present in the X-ray difflection. So basically, in the Heusler alloy, this 200 peak is not the fundamental peak. Okay, this depends on the atomic ordering. If the atoms are at their fixed position and they are not swapping their position, then you will get 200 peak. Otherwise, there are chances that this peak may not appear in the XRD pattern. Okay, so basically, this depends on the atomic ordering. Okay, and that's why it's not a fundamental peak, it's called the superlattice peak. Okay, similarly, if we calculate the structure factor for 111, okay, we will find that the structure factor for 111 is here, and finally you get this. So now, if your bi-atom is swapping position with the Z atom, okay, then again this is 0. And if this is 0, this will not appear in the XRD pattern. Okay, so this is also not fundamental. So this also depends on the atomic ordering. So if atoms are fixed at their Y-cup positions and they are not exchanging their sides, then this will appear. Okay, otherwise this will not appear. So these actually will give you different kind of a disorder. For example, if this is not appearing, it will give you B2 type disorder. If the 200 is and 111 both are not appearing, it will give you the A2 disorder. So basically, these peaks are only present when you have the atomic ordering. But there are some peaks, for example, 220 peak, 400 peak. These peaks will be always there. Doesn't matter that all the atoms, they are ordered to give the specific sites or not. These peaks will always be there. So basically, these are the fundamental peaks. Fundamental peaks in the Heusler alloy, while this 111, 200, they depend on the atomic ordering, or you can say additional atomic ordering. So these peaks here now, structure is same, FCC, but now they depend on the atomic ordering. While in case of the monoatomic, these were also the fundamental peaks. Okay. So they were always there. Because there was only single atom, even the one atom is going to the other atom position, still it's same atom. So it doesn't matter. So that's why they were the fundamental peaks. But now in this case, X, Y, Z, there are all three different atoms. And if they are exchanging their sides, then these peaks depends on their atomic ordering. Okay, so this is coming because of the additional atomic ordering. And similarly, you can see for the quaternary Heusler alloys. So if you calculate the form factor, this will come something like this. You can calculate the XRD, and for the 1 peak, again, you can calculate something like this. Okay, so all these depends on the how these atoms are sitting at the different position, if they are fixed. So if we conclude,